Hello, I am Jay, and now that we have discussed the pipeline overview, I'll dive deeper into the design discussions and the training process, explaining the reasoning behind the choices we made for each step. Model architecture is DistilBERT. The model we selected for this task is DistilBERT, a smaller, more efficient version of the popular BERT model. DistilBERT retains the core functionality of BERT while reducing its size by around 60%, making it much more faster to train and easier to deploy. The decision to use DistilBERT was driven by the need to balance model performance with computational efficiency. Transformer architecture, which is DistilBERT like BERT, is based on the transformer architecture, which is designed to capture complex dependencies and relationships between words in a sentence. This is crucial for tasks like sentiment analysis, where understanding the context of words is key to determine the sentiment for the task. For example, the word happy in a positive sentence would contribute to positive sentiment, while in a sarcastic sentence, the same word might imply a negative sentiment. The transformer self-attention mechanism allows to model learn such relationships effectively. Reduction in parameters: by reducing the number of parameters about 60% fewer than BERT, DistilBERT requires less memory and computational power while still maintaining competitive performance on NLP tasks. This makes it a perfect choice for a wide range of sentiment analysis tasks, especially when computational resources are limited. Training configuration choices. Now let's go over the choices we made during the training phase, where we fine-tuned the DistilBERT model to classify sentiment in tasks. Learning rate. The learning rate, which is one of the most important hyperparameters in training machine learning models, especially when fine-tuning pre-trained models in DistilBERT. Why we have used 2.92E5? We selected a learning rate of 2.92E5, which is a commonly used value in fine-tuning transformer models. This learning model is a good balance between coverage, speed, and stability. A rate that's too high might cause the model to overshoot optimal weights, leading to instability during training, while a rate that's too low would make the training process unnecessarily slow and inefficient. This particular rate allows the model to update its parameter insufficient this particular rate and sufficiently fast without causing instability in the optimization process. Choosing the right learning rate. Fine-tuning a model like DistilBERT requires finding a learning rate that would work with the data set, which is often done empirically and starting with a value in typical range, which is very good strategy based on the success seen in NLP tasks. Epochs. The number of epochs determines how many times the model will see the entire dataset during training. Why 3 epochs? We choose to train the model for 3 epochs for fine-tuning tasks, especially when working with a relatively small dataset. 3 epochs are enough to significant improvements in model's performance without overfitting. This choice was based on the typical number of epochs required to achieve good performance and task classification, task monitoring performance. Although the 3 epochs are generally sufficient, we continuously monitor the model's performance after each epoch by evaluating its accuracy on a validation set. If the accuracy began to decline, we would stop training early to avoid overfitting. Evaluation and validation. Evaluation is a critical and in understanding how well the model is performing during the training. Well, held out validation set. After each epoch, we evaluated the model's performance and on a held out validation set. This data set is separate from the training data, and it is used to monitor the model's ability to generate to new unseen data. By evaluating the model's accuracy on the validation set, we could check whether it was learning the task correctly or if it was simply memorizing the training data, a phenomenon known as overfitting. When to stop the training. The validation accuracy helped us determine when to stop the training. If we saw no improvement in accuracy over several epochs, we knew that the further training would not benefit the model and might leading to overfitting. The evaluation of the metric also helped us decide whether to adjust the learning rate or batch size in subsequent training runs. Loss function, cross entropy loss. The loss function is a mathematical function that helps guide the model towards the correct predictions by penalizing incorrect outputs. Why we use cross entry loss for binary classification tasks like sentimental analysis. Cross entropy loss is the most common loss function. It measures the difference between predicted probabilities and the true labels, positive or negative sentiment. The model to outfit possibilities for each class and entropy class qualifies how far these predictions are from the actual labels. Minimizing the loss function helps the model improve its prediction over time. And the one which is mathematical formula, the formula for cross entropy loss, compare the predicted probability for the correct class with the true class label. The loss increases as the model's predicted probability diverges from the true label, and it decreases as the model becomes more accurate. Batch size and samples. Batch size refer to the number of samples the model processes in one step before updating the weights. Why batch size of 16? So we choose the batch size of 16 for several reasons. Computational efficiency. There is larger batch size would require more memory, and we wanted to avoid overloading our system's memory, especially since we are training on a GPU with limited memory. A batch size of 16 allowed us to make efficient use of available resources while training the model. Speed and convergences. Smaller batches can lead to noisier gradient updates, but they allow the model to make more frequent updates to its parameters. A batch of size of 16 strikes a good balance, enabling the model to converge and relatively quick without sacrificing too much accuracy, training time, and consideration. Smaller batch sizes tend to speed convergences in early stage of the training, but they might require more epochs to reach optimal performances. On the other hand, large batch size can stabilize training, but they requires more memory location and processing time. So we found that 16 was an optimal choice for our available hardware resources and the task at the hand.